Okay, so in this particular video, we are going to see how one models these DC characteristics of a MOSFET, right? So what we have seen, and these models are very useful in designing a circuit, particularly let's say an analog circuit, or analyzing a circuit on using pen and paper. Because these models are obviously very simplified model, so which can help us do this analysis on pen and paper. And the more advanced version of these are what we talked about, are typically included in a PDK, right, which is the process design kit, which you will be using while one uses when they do design of a circuit using a simulation like Virtuoso and Cadence, which you use, right? Um, so the thing which we talked about is particularly we talked about the characteristic for a N-type MOSFET, which has a drain and source and gate, right? And this body terminal. And typically we talked about the two characteristics. One, we looked at the IDS versus VGS, and also IDS versus VDS. So S, which you see as a common terminal, is the reference terminal in this, right? So that means when you are applying a battery or a voltage, it's applied between your terminal, like gate or drain, and between gate and drain, sorry, gate and source, and between drain and source. So that is the terminology which, or how we are applying these voltages, and we are measuring the current between drain to source. So that is the, and then when we looked at the characteristic, we saw that in terms of VGS, we see that there was no current till certain point, and after a point which we named as threshold voltage, you see appreciable current flowing through the transistor. So that is what we could demarcate as this is the on, or sorry, off region, right, or cutoff, which we call it. And this is the region where your transistor is on and there is a channel, right? So that is how we are saying that below threshold, there's not appreciable charge in the channel to flow, but above threshold, there is charge to flow. And what makes it flow is the VDS. So that's why we put in some VDS so that we get a current. Now, if we were to look at the VDS dependence, that means we have to first make the transistor on. For that, we put the VGS minus VTH to be greater than 0, right? And so, and this voltage is what we see typically is known as also the overdrive voltage, VOV, which is just the VGS minus VTH. So we see that if the VGS is greater than VTS, that means the transistor is in on condition. Then if we apply VDS, the current changes first linearly, and after a certain point, it saturates. And this point is what we termed as the VD set, which is after the your current saturates to a value, right? So that is what we saw last time. And now what we would be interested in is to how to model this in a IDVG or IV characteristics, so that we can use those models to evaluate or analyze the transistor circuit and design such circuits. That is the idea. So also let me summarize the characteristics for a P MOSFET, so that for the P MOSFET also, if we see the terminal we see is the source terminal. The current is between source to drain. And I think the idea is very simple once you get um, accustomed to that, everything is defined now as the reverse of what was defined for NMOS, right? So still the source is the reference terminal, but what we define now, because the source, everything is subtracted out of source. So that's how you see the VGS as negative, right? Because we saw we need negative charge at the gate to bring in positive charge. And that is the reason that why you see the threshold voltage for P-type MOSFET is negative, because you need to have negative VGS applied for these MOSFETs, while for P MOSFETs, VTHN was positive, which we can see from the characteristics also, right? So if it is negative, then you would see sometimes when if we are, so now let me first plot this with VGS, how it would look like. So if you were to see this IDVG, so now which current are we looking at? We are looking at IST, right? Because that is what the current, and then we are looking at, suppose if we are looking at with VGS, then we know that when there is a negative VGS applied, only then there is a current. So that's why you would see a characteristics which is increasing when it crosses a certain threshold in the negative direction, and which is your VTP, right? This is the thing. This same thing we can also plot. I'll just plot here so that you understand. Rather than VGS, now as we looked at, if we use the opposite convention of VSG, then everything remains same, right? So we can then define it the similar way we define NMOS. And then this thing now, because it becomes positive, we just only need to take the mod of this voltage. So that would give us this positive quantity of the threshold voltage. So then we can say that now when our, for this, the VSD is greater than 0, right? And these two regions we can see when VSG minus mod of VTP is greater than 0, then our transistor is on, right? Similar way, we can also draw the characteristics for when we want ISD versus which one? VSD. So we just reverse the terminology, and we know that now we are plotting for a condition when VSG is greater than mod of VTHP, right? So for this condition, we still see that this would be the same characteristics, and this would be nothing, is just VSD set. That is your. So that means that everything is same. If you see in the characters, when you reverse the the terminal nodes, right? Instead of VGS, when I say VSG, and instead of VDS, when I say VSD, it just follows through, right? So now if we were to model these characteristics, how would we go about modeling it, right? Because we see we have the characteristics. Now it's just coming up with a mathematical model so that I can, when I solve for different circuits, I can use those equations, right? So that is what the very zeroth order model can help us do. Order IV model. And I think some of you may already know this model. So if we see the observations from this, one thing we clearly see is that, so we can derive this model also from physics, which is not, which is probably you would be seeing in other courses which are based on semiconductor physics. In this, we would be just writing it based on the observations from the characteristics which we are having, right? So first thing is when we are saying that when VGS, so this I'm writing for NMOS, right? When VGS is less than VTHN, right? That means my current is nearly 0. So there is no model needed, because you would put your current is so small. That is what the understanding is, and you can check that easily with your PDK or the simulations that you would be doing in few assignments, that your current is very small when it is below threshold, right? Compared to the current when it is above threshold. Now, so that means the model which we are actually derive or we are trying to form is for this condition when the transistor is on, right? Now if the transistor is on, we saw that there are two regions where this is dependent, right? So one is, first we see the observation that when it's above VGS minus VT, your ID increases with some polynomial function of VDS, right? And that is what brings to the first model, that your IDS is proportional to this VGS minus VT, and when we see closely, this is quadratic relation which it follows, right? So this comes as a result of it, the IDVG characteristics. Now there is a proportionality constant which we'll look at later. Now one can now say, okay, if that is the case, but where is the VDS dependence, right? So then we have to put in the VDS dependence. So to put the VDS dependence, we can see that initially we see that it actually increases linearly, right? So there has to be the current, this is anyway increasing exponentially, but we need to include the VDS dependence linearly. Now the question is, even if we make it linear, you see that after a while it becomes constant, right? This is not remaining linear. That means this is also, it from a linear curve, it changes to some parabola, right? That is the thing which you can see in this. So if you see IDVDS closely, you can see initially it looks linear, but then it turns into parabola so that it saturates. So this part is taken care by another term which we can add here, which is your VDS square by 2. Okay. So this would take in that part. So now you would see, if you were to plot this for a curve which is VGS greater than VTH, if we were to plot this IDS versus VDS, what we would see is this IDS and this is your VDS, right? And then what we would see is that your current VDS, so suppose when VDS is very small, you can see easily that your this term VDS square term would be very small, right? So it would go nearly to 0. So then your IDS is what we said, it would be linear. Initially, it shows a linear behavior with VDS, right? So this is this part. Then we see that if by VDS becomes appreciable, this current cannot be ignored. So then it's a parabolic relation. So parabolic means it goes like this, and there's certain parabola, and then it would be going like this, right? So this is the part which would come because of the parabola of VD square term. Now the question is that this is not correct, because what is we want is this, right? This is the saturation, because that's what our device shows. But the modeling is not able to take care of that. So that means now how would we correct this model? That means if I want to calculate that where it saturates this current, the only thing I need to do, because I know that at this point of wherever this maximum is, or this slope changes, the slope of this equation becomes 0, right? So that means what I see at that point, that my del ID by del VDS becomes 0. And where does it become 0? Where it saturates, right? Or the parabola reaches its peak. So then if I were to differentiate, I could see this becomes VGS minus VTH square, and this becomes 2. Sorry, there has been one problem, I think. Yeah, this relation, because there cannot be two. If we see that this is proportional to VGS minus VTH square, we clearly see that the VDS has to be multiplied with VGS minus VTH. Okay, so that is the one part which we can see from there. Okay. Yes. Okay. So that means now we will see, if we were to use this, that this becomes equal to VDS divided by 2, and that becomes equal to 0. So then your VDS, when it tends to VGS minus VTH, then your current, what happens to IDS? IDS becomes equal to IDS. So from that, what we can say is that my VD set, which is what the point we showed last time, is nothing. It's VD set is equal to VGS minus H, right? So now if I know that my current saturates at this point, then I can put this VDS value in my formula of IDS. So IDS then becomes proportional to, and this is the set I'm calculating because I'm calculating at VD set. VDS is equal to VD set, right? This VGS minus VTH become same, and VDS we just need to put VD set. And when we put VD set minus VD set square by 2, right? And if I put the value of VD set, this would become VGS minus VTH square minus VGS minus VTH square by 2, which would be proportional to VGS minus VTH square. Okay. And this is the similar thing which we saw when we were looking at the on state. Okay. So that means what I now see is that in saturation, my current, this is a very important characteristic which I see, that my current is proportional to VGS minus VT whole square by 2. Right? Now, if we put the constants which we get from the derivation, we can see that this would be coming as some of the factor mobility which defines the flow and the charge control, because there was a capacitance as you saw, W by 2. L2 is coming from here, and this is VGS minus VTH. So this is the ID set, and if we were to write IDS, this is when your VDS is greater than equal to VD set, which is nothing, which is VDS is greater than equal to VGS minus VTH, or VDS is greater than equal to VOV. So that means if a transistor crosses a threshold, the effort, let's say, of the VGS is wasted in the threshold. So the VDS which appears is the VDS has to be more than the difference of the two, right? That is the basic idea which we see here, right? So because the VDS is the potential which is between drain and source. And if the other condition, when we see the VDS is less than VD set, for this condition we saw that IDS would follow mu on Cox W by L. The 2 is not there because we need to have VDS dependence for when it is okay. So that means now we see the model is region dependent, right? So needless to say, in both cases you have VGS which is greater than equal to your VTHN. So that is the case for both of them, right? For this case particularly, we see the VDS is less than VD set. So then only this model is correct, right? And this is what we say as the saturation, and this is your linear current. Okay. And in case of PFET, this would be just change, the sign would change and everything would remain same. Just we will swap the source and the other node. So then we will say that in linear region, so we are writing for PFET, right? Your ISD become equal to now mu P Cox W by L. And what would we do? We just reverse the node, right? And instead of VTH, we put mod of VTH because now the VSG is positive, right? So we are subtracting a positive quantity. Same thing we do with the VSD square. So it's quite convenient once you swap everything, right? You don't have to deal with the negative signs which appear if you were to take in the with the source reference, like putting the gate first, right? So then this becomes in saturation. You will see your current becomes to L, and this has become VSG minus mod of VTHP whole square. And this is for a condition when your VSD is greater than equal to VSD set, which is nothing, which is equal to VSG minus mod of VTH. Okay, so these are the basic equation one would start to model. Okay, and one thing which you may see as an addition into this equation which we will use is some observation which we will try to model in the IDS versus VDS. So till now what we were saying that the current saturates, right? And this is what is showing you the VDS independence in the saturation currents, right? That is what the effectively you see. This is the ID set. But when you do this characterization for technologies, let's say like 180 nanometer and below, you see that this is not true. This is not fixed. That means there is the slope changes, but there is still some rise with the VDS which you are having, this linear rise. Now the question is, do I need to include in the model? Yes, if you want to take care of this, which is called something as the channel length modulation. So I'm not going into the physics of this. But what is the effect of this is that the current in the saturation region increases linearly with your VDS. So how do I model? That is what would my model change substantially when I do that? No. What do I need to do is I just need to put in one more term. So let's say in my, for NFET, I'm modeling NFET with CLM. So I call it channel modulation, right? Which is what typically we would use. You would see that you have to just modify because you didn't have any VDS dependence in saturation. So what you need to do is you need to put in one more term which is dependent on obviously some factor, which is a factor we are putting called lambda. We call it CLM parameter, right? So this is your channel modulation parameter. But what you can do with that is now you see that your lambda decides how much this is increasing with the VD, right? And you see that it is linearly increasing with the VD. And this is for the case when VDS is greater than VGS minus VTH, right? So for that case, we see that we can model this part by adding or multiplying with a simple term. The same way you would do this for the PFET also, that you multiply with the lambda VSD, right? So then you would have the CLM on there. Now this factor, one can see that how one obtains. So this is typically given by the technology, right? So you'll see that in your PDK and your files, when you do simulations, you will be able to see how much this lambda would be because it's dictated by the technology. Okay. So this is all about models which are needed when you want to do any DC analysis of these MOSFET based circuits, or you want to design the circuit and you want to analyze that if it gives the functionality which you want. This is the first thing you would want to do.